All right, question 6. The sketch here shows a book with a weight of 12.5 newtons at rest on a wooden board. The board is propped up at an angle of 15 degrees to the horizontal of the tabletop. So that's basically saying that this right here is 15 degrees. Okay, draw a free body diagram for the book. Okay, so again, free body diagram, always from the center of the mass. We have force due to gravity, pulling it down, or the weight pulling it down. Our normal force is perpendicular to the surface. Here we have force due to friction. In this case, because the book's not moving, this is going to be static friction. And yeah, because the force is the book's not moving, that's the force kind of holding it up. This is going to be equal and opposite of our force, or it's going to be equal to our force of gravity parallel. Yeah, and opposite, so that's pushing it back. Now we'll use that free body diagram to help us answer the questions for parts B, C, and D. Okay, so calculate the force of static friction for a book at this angle. And so again, what we're really looking for, we want to draw our second triangle to kind of find out what we're looking for. So these are the ones we did last week before we kind of started on the, or 2 weeks ago before we were off. So FG is always down. Okay, our FN is over here. Here, this is FG perpendicular, and then this would be FG parallel. And our angle is 15 degrees. This right here is our 90 degrees, making our force due to gravity, or our weight, is always going to be our hypotenuse. And so we know Fg from up here is equal to 12.5 newtons. So we're now looking for our Fg parallel. Okay, so that's our opposite, so we're going to use sine. So sine of 15 degrees is equal to opposite Fg parallel over adjacent, which is Fg. Actually, we'll just put in the 12.5 newtons. So we got for Fg parallel is going to equal 12.5 times sine of 15. Fg parallel would then be 3.24 newtons, which we got here. And so again, our Fg parallel, that's the force pulling down here. Okay, there is some gravity pulling the book down. Our force of static friction is pulling the weight of that book, or keeping that book from moving, so it's equal and opposite to our Fg parallel. So our force of static friction is going to be the 3.24. So they are equal. Okay, if the angle of the board is increased to 28.5, the book just begins to slide down the board. Okay, find the value of our force of friction static max for the book. So really it's the same thing. Make our new triangle here. Same triangle, but now we have a different angle, 28.5. We're looking for the same thing now that our force of friction static max is when the book just starts moving, so it's going to again be equal to our Fg parallel. So static max is going to equal Fg parallel. So now we can solve for it the same way we did up here. So sine of, now we have 28.5 is equal to our Fg parallel over 12.5. Fg parallel equals sine of 28.5 times 12.5. That's our force of friction static max is equal to 5.96 newtons, and that's what the answer should be there. Okay, and then if the angle of the board is maintained at 28.5, would you expect the speed of the book to increase as it slides? And explain considering the idea of kinetic friction. Okay, and so for this one, we are expecting it to slide because now, like it says, it starts to move with that much friction. Okay, once we overcome our static friction max, again, the kinetic friction is usually less than static friction. So that means we're going to have an overall F net pulling the book down the angle, which means that, yes, we'd expect that if we have an F net, then we expect acceleration. So kind of just writing down what I said here. So if our F net's equal to our force of gravity pulling it down minus our force of kinetic friction kind of keeping it up. As long as we get a positive number as our F net, then we're going to have a positive acceleration. Okay, so forces of friction, they are predicted approximately by the equations for static friction and kinetic friction. So for force of static friction, our force has to be greater than or equal to our coefficient of friction for static friction times our normal force. Okay, kinetic would be our coefficient of kinetic friction times our normal force. Okay, we use the symbol Greek letter mu, so it looks like a U with kind of an extra little line added in. Okay, to represent the coefficient of friction, and then we either write the S or the K representing static or kinetic. Because both sides of the equation will have units of newtons, okay, our coefficient of friction has no units, it's said to be dimensionless. Okay, and then again, Fn is our normal force between the two surfaces in contact. Okay, for an object resting on a horizontal surface, Fn is equal to the weight of the object. If it's on an angled surface, our Fn again is parallel. So like when we had the book, and this was 28.5, our book was sitting here, our Fn was up going that way. And so we'd have to use our trig to actually solve for what Fn is. Okay, and then summarize the points listed in your text on page 183. These are the points that it's talking about. So the equation for static and kinetic friction are not fundamental laws. Instead, they're approximations of experimental results. So again, the coefficient of frictions are kind of experimented on, and they have a bunch of examples here further down on the page. Okay, the equation for force of friction static max, okay, is equal to coefficient of static friction times our normal force, and then kinetic equals coefficient of kinetic friction times normal force. It cannot be written as vectors because the vectors for force of friction and normal force are perpendicular to each other. So really just use scalar values. You don't need to give a direction of forces. Just be aware of like when you're trying to find F net, which forces are acting in which direction. For both coefficients of friction, they're proportionally constants and have no units. We already talked about that. And then for a given pair of surfaces, the coefficient of static friction is usually greater than the coefficient of kinetic friction. So once you get it moving, it usually moves easier than it was originally when you started moving it. And then the coefficients of frictions depend on the material forming the contact surface. So how smooth or rough it is, whether the surface is wet or dry, the temperature of the two surfaces, and there could be other factors. And so you can kind of see in this table the different examples of coefficients of friction. Again, like if we look at like dry asphalt, has a higher coefficient of friction than wet asphalt, and so on.